So let's work on our problem cost. Again, you're given an undirected graph with edges with distinct positive weights, and the graph has at most 100,000 nodes and edges, and you're asked to calculate the sum of the distance between every pair of nodes, where the distance is defined as follows. You fix a certain pair, A, B, for instance, these two, and you sort the edges in increasing weight. You remove them one by one until the two nodes are disconnected. And then you sum the weights of the edges you removed from the graph. That's the distance between A and B. So, for example, the distance between these two nodes would be just 1 because after we remove these edge, the two nodes are already disconnected. And the distance between this pair of nodes is actually 3 because we have to remove both edges. Okay, so because the number of nodes is so large, it's at most 10 to the 5th, we know that we can't even iterate by every pair of nodes. So that already discards this approach of trying to for each pair, efficiently calculate the distance between those two nodes. So what can I do in this case then, if we can't even iterate by each pair of nodes? Well, if we follow the distance calculation procedure, you may note that there aren't exactly many distinct distances between a certain pair of nodes, because there are only n plus if m is the number of edges. If m is the number of edges, there are only m plus 1 distinct moments in which we can stop in the procedure. We can either not remove any edge, in the case the two nodes are already disconnected in the original graph, or we can stop after removing the first edge, or after removing the second edge, and so on until the last edge. And each moment of these gives us one distinct distance between the pair of nodes, but there are only those ones. So we may try to calculate them by grouping the pairs of nodes which have the same distance, which leads us with a more reasonable number of options to consider. So okay, let's try to do that. The most natural thing to do would be to follow the procedure, and in each step, which means in each edge we're removing, we check to see what pair of nodes would we have the distance calculated right after removing that edge. So in the original graph, we already have, let's add a fourth disconnected node here, just to illustrate the distance of 0 case. So the first thing we would have to do is to consider the pairs of nodes that are already disconnected from each other. We would have to run a depth first search or something like this in order to calculate connected components. And then with a bit of combinatorics, we calculate the number of pairs which are already disconnected from each other. Then we would move on to removing the first edge and checking how many pairs are now disconnected. We can maybe take the difference between this number and the previous number to see how many pairs were disconnected by the removal of this edge, and so on and so on. But this procedure in the middle of calculating how many nodes are disconnected, how many pairs of nodes are disconnected, you can try to make that efficient, but it will turn out to be hard. So what does that mean? Does that mean we should not use this approach of grouping pairs of nodes by the distance? Well, one insight that is not usually, but sometimes useful, is to try to invert the problem, because sometimes the inverse problem is much easier and equivalent to the original one. So what would be the inversion in this case? Instead of starting with the whole graph and, as the procedure tells us to do, remove edges incrementally from it, let's start from the empty graph and then add edges to it in the inverse order in which we would remove them. So in this case, we would have 4 nodes. And instead of, for example, first calculating how many pairs of nodes were already disconnected, in this case we already know how many pairs are disconnected, right? It's much easier. All pairs of nodes are disconnected because there are no edges in this graph. But now, when we add, instead of removing the lightest edge, we add the heaviest edge, which turns out to be this one with a weight of 2. What happens? Well, because we just inverted the problem, we're not looking at how many nodes were disconnected by the addition of this edge, which doesn't happen, right? But rather, we're looking at how many pairs of nodes were connected, are now connected after we add this edge. And why is this important? Well, it is important because we just inverted the procedure. If we added this edge and a certain set of pairs of nodes are now connected, we know that the edges that will be added later in the process do not influence these pairs of nodes, which means that in the original procedure, until we remove this edge, the pairs that are now connected will remain connected. So we know that the distance of this pair of nodes in this case, but more generally, of all the pairs that are now connected after we added this edge, we know that the distance between them is exactly the sum of the weights of the edges, which we did not remove up to now, plus the weight of this edge. Because after we remove this edge, then yes, then these pairs of nodes are disconnected. So how many pairs of nodes are now connected after we added this edge? Well, in this case, because an edge can only connect 2 connected components, it can only join 2 connected components that were disconnected from each other, we only need to know how many nodes are in the same connected component as this node, and multiply that by the number of nodes that are in the same connected component as this other node. In this case, there is one node in each of these components, giving us only 1 pair. So, with a distance of 3, which is the weight of this edge which we are about to add, plus the weight of this edge, with a distance of 3, how many pairs do we have? We have exactly 1 times 1 pair. After adding this edge, the next edge to add would be this one. And now, when we just added this edge, how many nodes are now connected how many pairs of nodes are now connected that were disconnected before? Well, let's just follow the procedure of counting the sizes of the connected components in each endpoint of the edge. And in this endpoint, there were 2 nodes in this connected component, whereas in this endpoint, there was only 1 node. So with a distance of 1, which is the number of pairs which become disconnected when we remove this edge, we have 1 node on one side times 2 nodes on the other side, which means that when we remove this edge, we're disconnecting 2 pairs of nodes, which is this pair and this pair. And these 2 pairs of nodes, because of that, have a distance of 1 between them. So now that we added all the edges, oh no edge. So now that we added this edge, we don't have any more edges to add, which means we're done with our algorithm. And now, the only missing detail is which kind of data structure would be maintained in order to know whether two nodes are already connected to each other, and if they are not, how many nodes are on each side of the edge, on the edge we just added? Well, it turns out that a simple disjoint set union or union find data structure can answer all these queries efficiently. So our procedure would be to start with the empty graph and the sum of all of the edges in the graph, and then incrementally add edges from the heaviest to the lightest, and every time we add an edge, we check if the two nodes which that edge joins are in the same connected component, which is just a query to the union find data structure. If they are not, if they are, that means that removing this edge does not change anything in the graph anymore. But if they are not, if they are in distinct components, that means that we just found a certain set of pairs of nodes which have a certain common distance between them. And the number of pairs in that group would be the size of the two connected components which are about to be joined, which are easy to calculate using this data structure we are maintaining. And more than that, again, using the union find, we can easily join the two connected components. It is the union part of the data structure, right? And we can, of course, update the size of the joint connected component, this component's form, because we just need to add the size of the two already existing components. And when we pass on to the next edge, the distance will be reduced by the edge we just processed. So in this case, we start with a distance of 3, and then when we add this edge, the next distance will be 1, because we've removed the weight of this edge. After we process this edge, the distance will be 0. But note that we don't actually have to process the weight of 0, because it will not count in the answer anyway, so it doesn't matter to try to count how many pairs of nodes have a distance of 0 between them. So that would be our algorithm, and using this data structure then, we can solve the problem in all of m log m, because basically we'll need to sort the edges in the beginning, and then the same cost will apply in the second part, because for each edge we'll have a constant number of operations on our union find data structure to query and update it. And so this is a totally reasonable complexity for this problem. And yes, so that's our algorithm, our solution for the problem cost.